As laptops continue to improve, is it possible to create one yourself? Perhaps with a 4K AMOLED display, a wireless mechanical keyboard, an anodized aluminum chassis at 17.5 millimeters thick. This is Neon E.
Now you might be wondering why you'd want a wireless keyboard in a laptop and have so many other questions, and don't worry, I'll get to that. In designing Neon E, I wanted to match as many qualities of a modern thin and light laptop as possible, while also making as many parts from scratch as I could. Laptops aren't that complicated after all. With enough simplification, you can break it down into 4 systems.
Compute encompasses the CPU, GPU, RAM, storage, I/O, and the operating system. Pretty much what you'd consider for a PC. For power, there's the batteries and the charging implementation. The peripherals include the keyboard, touchpad, power button, and speakers. And lastly, the physical aspects comprise of the chassis, hinge mechanism, and the design language of the device itself. Breaking the system up into chunks, I tried finding the most optimal solution in each. I wanted to target a few goals: the RK3588 system on a chip, an ultra-thin wireless mechanical keyboard, a 4K 13.3-inch AMOLED display, field-oriented controlled brushless DC motor input, a high-accuracy trackpad, a roughly 60 watt-hour battery pack, and an anodized CNC'd aluminum chassis. Now let's go back to the compute system. The most important part is choosing the CPU, or in our case, the SoC. The chip selection process seemed almost too easy. Intel and AMD's offerings wouldn't be possible without signing a thick stack of NDAs to get access to the development details. With the x86 market out of the picture, the next best solution is ARM64, like you see in the up-and-coming Qualcomm and Apple laptops. Okay, well that's not exactly true. Using Apple and Qualcomm would run up the same issues as Intel and AMD. But there's other solutions. After doing some research, I came across this. Alright, so I have the datasheet of the RK3588 printed out here, and there's a few things that I want to point out, and mainly the Cortex A76 as well as the Cortex A55 processor. So both of them are quad-core. Add them up, you get 8 cores on this CPU. And for the GPU, you have a Mali G610, which is enough to run Minecraft at 4K, really low settings around 30 FPS, which is more than enough. And you also have the addition of a nice neural processing unit. So in this age of AI, you get a lot of AI capabilities for a chip like this. For your video output, also known as your display here, it can output up to 8K, as well as an embedded DisplayPort version 1.4 interface, which will be very important later on, as well as dual USB 3.0 here, which supports USB Type-C as well as DisplayPort. And this is kind of hard to read, so let's take a look at the block diagram. And on the block diagram, we have the A76 here, A55 here. We have our NPU, our Type-C ports. Is also PCI Express, which you can see more easily here for connectivity, so we'll be using that for the Wi-Fi card and the storage, as well as all the necessary system peripherals, the multimedia interfaces, which include the embedded DisplayPort.
These specs look good enough for a modern laptop. Great. However, it's incredibly expensive to build an HDI or a high-density interconnector board for the RK3588 or any other symbol chip. For I only had a few months to work on this project, so a system on a module, or SOM, like the Raspberry Pi Compute Module 4 was the best option for hardware compatibility and increasing the chances of a functioning system. Choosing an SOM meant that I knew at least some part of the compute system would work initially. Looking around for an RK3588 SOM, I came across the Friendly Elec CM3588. Looking through the documentation, the schematics, the Linux drivers, and evaluation board, it gave me a lot of confidence. And Linus also published a video using it to drive a NAS just a few days later, reaffirming my option. Now let's go back to embedded DisplayPort. It's crucial for this project as nearly all modern laptops use the EDP protocol to drive the internal display. Having a fully compatible EDP port allowed me to put pretty much any display on the market. I hopped on paintlook.com, a website meant for large display resellers, and filtered by size and resolution. Looking at 4K and 13.3-inch displays, I came across a few OLED options from Samsung that caught my eye. I settled on the 4K AMOLED 13.3-inch display, the ATNA33TP11 to be exact. Cross-referencing stock on Taobao, it seemed to be the one with the most brand new stock, since going OLED meant risking burn-in and other potential nuances. But thankfully, the seller sent verification videos before shipping them. You know how I was foreshadowing about the display evaluation? Well, it turns out that driving a 4K display over embedded DisplayPort is a very difficult task signal integrity-wise. And I have both evaluation boards pulled up on KiCad. But first, let's talk about how they work. I didn't want to design and buy an entire development board just to test the display, so I piggybacked on the CM3588 NAS SDK, or the development board. The HDMI connector is actually multiplexed into a Samsung IP core deep within the chip silicon. After writing some Linux device tree definitions, you can have the HDMI connector output EDP signals instead. That's why the HDMI connectors are on the display evaluation boards. Then the signals are routed into the EDP connector format. On the left side is the V2 short, and on the right side is the original V1. And as you can tell that there's a V2, the V1 probably didn't work so well. And I spent a really long time figuring out why, and it comes down to signal integrity. So let's do some digital frequency analysis. Consider the bandwidth of the system. With 4K resolution at 60 Hz, using 8-bit color, you'd reach just under 12 gigabits per second of bandwidth. Accounting for overhead, the bandwidth is closer to 14. DisplayPort defines the high bitrate 2 protocol, or HBR2, to be 5.4 gigabits per second for 4 concurrent channels, which is roughly equal to our calculated bandwidth, while again accounting for overhead. Taking a deeper dive into the HBR2 bandwidth, we need to first account for color encoding overhead. We get 4.32 gigabits per second as our final answer. And since bits are just zeros and ones, your frequency here is the same, 4.32 gigahertz. This is what an embedded DisplayPort connector looks like. There's 4 lanes of data transferred through differential pairs. When you start reaching frequencies in the mega or gigahertz, you need to start considering impedance matching. The small reflections or imperfections of the signal path become amplified at such high frequencies. Think about it like a modification to the classical water pipe example for electronics. Imagine the green pulse as a sudden jolt of water pressure, and the resistances as the thickness of the water pipe. If the pipes are all the same thickness, then it's all smooth sailing. However, if one part of the pipe, or in this case the resistance, is different from the rest, the sudden change in thickness of the pipe will create turbulence, or in our case, reflections of the signal. This causes the signal integrity and strength to drop. Going back to the display evaluation boards, the chip and the display have inherent impedances of around 100 ohms, and it's our job to make sure that everything connecting between the display and the chip, such as our evaluation board, is also 100 ohms. And we can do this by making sure the distance between the traces and the surrounding grounding planes of the traces work out to give us that expected impedance. That's what you see here. I won't go over the calculations, but if you're interested, I highly encourage you to check out other resources. I really wanted to take this opportunity to explain impedance matching at a high level, but that's not why V1 didn't work. The actual reason still had to do with the high frequencies, but it comes down to signal loss. In the first version, I used a female HDMI connector, meaning that going from the development board to the V1 display evaluation through a male-to-male adapter. This made it just barely too lossy for it not to work. But with V2, I soldered on a male HDMI connector directly onto the display evaluation board and removed every unnecessary part, cutting down on the actual physical length. With all that, I finally got the display running. This is the motherboard version 1.0. Now with everything defined, we can move on to designing the PCB itself in KiCad. And I had to go through 3 revisions in order to get to the final PCB that's currently inside the laptop.
At the start, however, I needed to figure out the general layout and dimensions of the board. Thus, I opened up PTC Onshape and began CADing the chassis. Yeah, I know I'm jumping around a lot and I apologize for that. Now, from great past experiences with JLC, I decided to venture into their new CNC offerings for this chassis. It offered me lots of freedom in terms of design choices compared to 3D printing or laser cutting, and CNC aluminum would offer a high quality feeling material and coating from the anodization. The section that takes up the most area in a laptop are the batteries. I wanted to make my own power system, which I'll get into later, so I started fiddling around with potential lithium-ion cell sources for a few days. Shipping battery cells from China would take too long, so I limited myself to American domestic sellers. The only major player I found in this space is Battery Space, or AA Portable Power Corp. Finding the best balance of height, power density, and charge-discharge performance, the PL546710002WR prevailed. In the end, I chose to place 4 of the 4250 mAh lithium-ion batteries in series. These cells are only 5.7mm high, and 4 of them fill up just around half of the lower chassis. Tangent over, this leaves me with around 90mm of board width to work off of. Implementing all the features on the final mainboard would stretch this video way too long, so here's a quick overview. A printed circuit board is really just a bunch of very thin copper wires on a piece of fiberglass called FR4. The green is what's called the solder mask, which is heat resistant and allows solder only to stick to the parts of the solder mask it doesn't cover. Within a circuit board are a bunch of layers of copper, with the extra parts milled away to create the final PCB. The main board has 6 layers since it has higher complexity from the high frequency systems. Most boards are usually just 2 to 4 layers. Now, when designing most circuit boards, they're split into sections based on frequency and power. On this one, there's the high frequency, high power, and medium frequency sections. You want to isolate them because high power parts generate a lot of noise that the high frequency sections are sensitive to. Before all that, you need to make a schematic. It outlines all the electrical components inside the PCB. These board-to-board interconnects allow for a total of 400 connections to the RK3588 SoC, including everything from EDP to simple GPIO. Within these blocks are smaller schematics for specific purposes like USB-C, PCIe, system functions, and more. And for those, you choose your chips and supporting passives, including the decoupling capacitors to smooth out voltage entering the chip and resistors pulling signals high and low. For a board like this, you'd also want to put diodes shunted to the ground for electrostatic discharge, or ESD protection. Now, some chips include the TPS564257 buck converter to step down the battery voltage into a more usable 5V and 3.3V rails, the FUSB302 to conduct complex USB handshakes, the PI6C557 for generating the PCI Express clock signals, and the CH334F for internal USB connections. Now, the schematic editor links up to the PCB editor, where you can start quote-unquote routing or drawing the physical traces for each connection. There's around 1,600 total connections here. Although there's some really cool options for reinforcement learning PCB routing like quilters, they're not quite powerful enough to make a circuit board of this complexity. Well, at least not yet. Now, with everything wired up, you choose your physical components from JLC PCB's warehouse so they can be assembled for you, pay, and you get assembled boards a week or so later. After figuring out everything that's broken, usually some really dumb mistakes, it turns on. Now, time to run the operating system. Getting Windows, or heck Mac OS to run would be a project on its own, so I explored the Linux realm. Joshua Reek's Ubuntu Rockchip install combined an out-of-the-box experience with lots of optimizations. I would need to extensively modify the hardware definitions to match my motherboard, however. But surprisingly, the friendly Elec Nano PCT6 is somewhat similar in hardware, and that Linux image just booted. But to get the peripherals working as intended, I still had lots of work ahead. Recompiling the kernel per modification would take way too much time, but since nearly all the work I needed to do was abstracted in the device tree or DTS hardware language implemented within U-boot, I took advantage of its system-agnostic nature. U-boot is the bootloader, which loads the operating system upon startup. I'd write the device tree on my daily driver MacBook, virtualize ORBStack into an Ubuntu instance to compile the device tree binary, and send it over to the mainboard. By configuring Ubuntu to boot from a custom binary, running U-boot update regenerates the bootloader configurations with every new binary. Much faster than compiling the kernel each time, and also much easier to maintain. That's how I did the software development: display configurations, PCI Express, USB, and other low-level system tweaks. The rest of the operating system is just a bog standard Ubuntu 24.04 LTS with Linux kernel 6.1. This entire time, I'd been running the motherboard off of a benchtop power supply. Now it was time to get it running off the batteries.
We got our batteries from before, adding up to 62.9 watt hours, and pretty good in similar other laptops. Now we just need to figure out how to charge them. The idea behind the Powertrain is pretty simple. You put the batteries in series to get 4.2, which is the peak voltage, times 4, so 16.8 volts. You get a battery balancing chip to make sure the voltage in each cell remains similar, and charge them up with another chip that gets power from the USB-C. So that's what I did. The system is designed for up to 20 volts USB-C, aka 100 watts, and passes into the BQ257013 charging IC. The batteries are balanced with the BQ77915, and the power is tracked with the LTC2943 to give us a state of charge percentage. I popped in an ESP32S3 module for the controller for everything, and set it to production. And it mostly kind of worked. Fixing some of the traces and slightly misbehaving ESP32, I sent out a second revision.
After writing a bunch of embedded drivers for those 3 chips in Arduino, since there was nearly no sample code for them, fixing some MOSFET issues that were much beyond me, I had the batteries charging.
I load tested it and finally plugged it into the motherboard for the first time. The USB of the ESP32 connects to the internal USB on the motherboard to feed power telemetry over UART. A Python script and a kernel module in the operating system forwards it into the battery service of the kernel itself to display it natively. So we have the motherboard working, powered by the batteries, but how do you control the laptop now? Let's talk about peripherals. The keyboard is really just an aluminum sandwich fixed together with screws around the edges. I had a crazy idea when designing Anyani for the first time, which was to have a removable keyboard. Imagine being able to pull out the keyboard and use it for anywhere else just as a regular wireless keyboard would. The PCB is similar to the designs I made previously with the Nordic NRF52840 running ZMK firmware. I soldered on Cherry MX ultra low profile mechanical switches, because since we're already balling out everything else, you might as well get the best on the market for keyboard switches as well.
The keyboard up to this point was pretty painless. The 1mm battery worked with my custom low profile battery protection board too, but things headed downhill quickly when it came to the keycaps. I already settled on the mechanical switches, so I had to find a keycap that would fit them. There's a lot of detail on these, as you can see. A normal FDM printer wouldn't have the resolution. In my first revision, printed by JLC, you can just see how small the lip is around the keycaps that exist to grab onto the switch mechanism. However, I wanted to use skin-safe SLA resin, since that would mean I could be typed on constantly. Thus, I got an SLA printer and Bluetech skin-safe resin, but I could never get the tolerances right. The keycaps would shrink and curve even days after extensive curing, and the keys would always get stuck and feel mushy. As a last resort, I got a 0.15mm nozzle for my Bamboo Lab X1 Carbon and optimized the settings on Orca Slicer to print with such. And with PLA, it just worked. Printing out all the keycaps and assembling for the last time, the keyboard was done. Moving on to the trackpad, it was pretty quick. I knew from the start that I wanted a good trackpad, so making my own with absolutely zero capacitive tracking experience is a no-go. Searching online, I came across the Azotec PXM0075 evaluation module on Mouser, and it had it all. Glass surface, multi-touch, and it just worked over USB. And it was only $35. However, the trackpad has now ceased production without many alternatives. With the keyboard and trackpad working, it was now time to put on the finishing touches. Roughly the same time I began the system design, I had sent a few CNC aluminum blocks off to JLC for evaluation with different anodization finishes. The dark gray anodization felt best, but I preferred the look of the matte black, so I settled on that. And I began catting out the rest of the chassis. I aimed for a robust and minimalistic look and a blend of my two favorite laptop designs, the Razer Blade and the MacBook Pro. Because of the removable keyboard, the bottom has no screws. Instead, the palm rest screws into the bottom chassis. Putting everything in the right place was just a massive jigsaw puzzle. Everything should have really had its own place, determined way ahead of time, but oh well, bad engineering. And the hardest part about the chassis was the hinge. I used Frameworks hinge because it had a 3D model, it could be readily purchased, and is already designed for a 13-inch laptop like this one. I constrained it on Onshape so that I could see the exact closing angles. And let me tell you, it was a battle to get the screen assembly to not hit anything while also covering up the rotational mechanism. Although I started considering thermals way in advance, hence the gap here for the heat pipe to go through, I still had difficulty fitting everything in. The distance between the bottom of the keyboard and the top of the heatsink is less than half a millimeter. The cooling is really constrained because I don't have the resources to make a custom heat pipe and fin solution. So I made a chonky full copper heatsink and a heat pipe connected to a fan. I think it looks pretty cool. I also added these PUI audio speakers to either side. Unfortunately, the kernel just didn't seem to work with audio, so I made a USB to audio converter board separately and passed it into an amplifier. I would have also made the amp, but I ran out of time. The power button is printed with a transparent PETG and a little power button board with a switch and LEDs, giving it that nice glow. As I reached final assembly, I used a mix of JLC selective laser sintering or SLS of nylon powder, like in the Formlab Fuse, and FDM printed PA6CF for smaller structural parts on the Bamboo Lab X1 Carbon. Putting it all together, I put it against my M3 Max MacBook Pro for a boot up drag race.
I'm powering these on in 3, 2, 1.
After all that, what is the mission? An anyon is a two-dimensional quantum particle that is neither bosonic nor fermionic. In the same way bosons collapse together in the lowest energy state, a laptop is compact and tightly integrated. However, it's distinct, and each energy level is identifiable, like fermions. And please, forgive me for this loose quantum comparison. Anyon is a laptop for anyone. Using it feels sleek, polished, and like a flagship device from a major company. Meanwhile, there are no secrets under the hood. Anyon is a mission in and of itself, to show that it is possible for anyone to make a nice, solid laptop. The power is in your hands.